We are discussing the 9701 question paper 4-2 of the examination series October-November 2024. We have already discussed question 1 to question 3 in our earlier video, and in this question we are going to start with question 4, 5 and 6 then. So let's go ahead with question 4 now. So here is question 4, and it's transition metal atoms and transition metal ions form complexes by combining with species called ligands. Now NaOH aqueous is added to an aqueous solution containing cobalt aqua water, that is cobalt complex with water molecules. A precipitation reaction occurs accompanied by a color change. Now understand, this is an aqueous solution containing an cobalt ion with its ligand of water molecules, and we are adding NaOH to the aqueous solution of cobalt complex. In this reaction, two of the water ligands, that is out of 6, 2 water molecules are each losing one hydrogen ion and are gained by OH minus, that is hydroxide ions from NaOH. Now state the color change seen in this precipitation reaction. Now if we go ahead and have a look at what is here asked in the question, we know it's an aqueous solution of cobalt. Now aqueous solution of cobalt is always pink in color, and if it loses 2 of its water molecules, then obviously it is forming water molecules as a byproduct. So losing water molecules, it will change its color to blue. So this is the color change, that is pink to blue. Okay, the next second part is complete the ionic equation for this precipitation reaction. Now we need to understand that we are taking a cobalt complex with water ligands, 6 water ligands, and we are adding NaOH to it. But it is clearly written that NaOH as a whole is not reacting, it's actually reacting with the OH of the NaOH, and that is removing out one hydrogen from 2 of the water molecules. So obviously cobalt is left with 4 water molecules, and if 2 of the water molecules loses hydrogen ion, then it's left with the OH, that is hydroxide. Now that is going to form the complex. So actually hydroxide ions are reacting, so I've removed out NaOH and in place we'll be writing hydroxide ions. Now if this is the complex, we know that cobalt is in 2+ state here, and if cobalt is 2+ state, and we know that the hydroxide is having a -1 charge, but then there are 2 hydroxide ions being left. Why? Because 2 of the water molecules lost the hydrogen ion, so there are 2 hydroxide ions. So this -1 multiplied by 2, so 2 plus and -2, overall charge of the complex becomes 0. So we are not adding any charge on the complex, which is here as 2 plus, but the product cobalt complex does not have any charge. Now if the hydrogen ion reacts with hydroxide ions, hydrogen ions from the water molecules are reacting with the hydroxide ions. As we already said, 2 of the water molecules loses, so 2 water molecules will be formed as a product because 2 hydrogen ions reacts with 2 hydroxide ions to form 2 water molecules. That's going to be the product. So hydroxide ion here gets 2 as a balance, and we get 2 water molecules as a byproduct. So this is how we complete the reaction. We are adding 2 hydroxide ions, a cobalt complex is formed with no charge, and 2 water molecules are formed. So this is how we are going to complete the ionic equation for this precipitation reaction, and these are the precipitates of cobalt complex formed. The third question is, this precipitation reaction can also be described as a different type of reaction. Now name this type of reaction. Now here we know that the hydrogen ion and hydroxide ions are reacting also to form the water molecule. So obviously this also can be called as an acid-base reaction, because here acid and alkali are reacting together. If we go ahead with the B part, here L is an uncharged tridentate ligand. Now L donates 3 lone pairs to a metal atom or ion. Now understand, L is a ligand which is tridentate. Now tridentate means the one molecule of L can form 3 dative bonds with the metal ion. Now that is why it is called tridentate. So L donates 3 lone pairs to the metal atom or ion. Now cobalt forms octahedral complex ion with ion E. Now complex formed is E with the ligand L. So what is happening? Understand again. Cobalt metal forms an octahedral complex E. So E is the complex ion formed when cobalt reacts with the ligand L. Now complex ion E has a 2+ charge. Now give the formula of E. Now if we know that L is a tridentate ligand forming 3 dative bonds, and if it is an octahedral complex, now octahedral complex have 6 total dative bonds. So that shows that the L used are 2. That is 2 L ligands will form 3 dative bonds each, forming total of 6. So we can write that cobalt is forming ligand is forming 3 bonds with the ligand. 3 ligand molecules are used to form 6 bonds. So should I write LO? L3? Yes. Now if we work out the charge, it has said complex ion E has a 2+ charge. So obviously if cobalt used here is forming 6 dative bonds with 3 ligands and the charge is 2+, then we can write it the complex formula this way with the overall 2+ charge here. Okay, identify the oxidation state of cobalt in E. Now L is neutral, so even if 3L is used, the charge of L is neutral and the overall charge is +2, then in that case cobalt should also have a charge of +2. That's why the overall charge is 2+. So oxidation state of cobalt in E is +2. So this is how we work out the oxidation state. Let's go ahead with the next sub question. The d orbitals of cobalt atom or ion present in E are split in energy. State the number of d orbitals that are at higher energy level and the number of d orbitals that are lower energy level. Now if it is forming octahedral complex and there are 5 d orbitals, with the octahedral complex, out of the 5d orbitals there will be 3 orbitals at the bottom and there will be 2 orbitals on the top at the higher energy level. So at higher energy level I would say that there are 2 orbitals, and at the lower energy level the d orbitals are 3. In an octahedral complex this is the sequence, but if it's a tetrahedral complex then the sequence will be reversed. That is, at higher energy level there will be 3 and at lower energy level there will be 2 orbitals of d. Now define the term non-degenerate d orbitals. Now non-degenerate d orbitals are the d orbitals which have different energies, or we can say different energy levels. So here we end with the definition of term non-degenerate d orbitals. Let's see what comes the next. In the C question, the mineral chromite contains a compound which has the formula of here given, where we have Fe, chromium with N number, and oxygen 4. The oxidation state of ion in Fe is a +2. It's given. The oxidation state of ion is +2 here. Now a sample of 4.18 gram of this compound is dissolved in excess of sulfuric acid. The resulting solution is made up to 250 centimeter cube. This is a solution F. So solution F is what? When this compound is mixed with sulfuric acid and made up to 250 centimeter cube, that is the solution F. Now all the Fe2 plus ions in 25 centimeter cube of solution F are oxidized to Fe3 plus ions by exactly 18.7 centimeter cube of 0.02 moles per dm cube of potassium manganate. Now one manganate ion reacts with 5 Fe2 plus. Assume no other oxidation reaction occurs. Now write an equation for the reaction of Fe2 plus and manganate ions in the acid solution. Okay, now it's clearly written that there are 5 Fe2 plus ions reacting with one molecule of a manganate ion. Obviously then it changes to 5 Fe3 plus ions. Now if we know that the oxidation state of 5 Fe2 plus is changed to 5 Fe3 plus, there is an oxidation change from here to here is plus 5. Why? Because each Fe is losing one electron to become plus one charge. One charge extra plus one is added. So if there are 5 such ions, total of oxidation state change should be plus 5. Now here we know that the manganate is in oxidation state of plus 7, and if it is undergoing a change of plus 5, there should be a minus 5 out of manganate. So manganese will change to 2 plus oxidation state. Okay, why? Because there is a change of the oxidation state of 5. So if Fe is increasing by 5, manganese should decrease by 5. So plus 7 changes to plus 2. Okay, now what about the oxygen atoms? 4 oxygen atoms present here, that will change to 4 water molecules. And what about the hydrogen here? That hydrogen, that is 8 hydrogen, will be used here as an 8 hydrogen ions, because it's clearly written that it is in the acid solution here. So this is how you're going to frame an ionic equation for the reaction of Fe2 plus with the manganate ions. Now if we go ahead with the second part, calculate the number of moles of Fe2 plus ions in 25 centimeter cube of solution F. Now we need to understand that first, if we have got the concentration and volume of manganate, we need to calculate the moles of manganate first from this values given, that is concentration into volume, that is 0.0200 multiplied by 18.7. Now that is in centimeter cube, so we need to convert it into dm cube by dividing it by 1000. So into 10 power minus 3 it is. If we multiply this, we get 3.74 into 10 power minus 4 moles. That's the moles of manganate. Now if we have a look at the ratio here, it is 5:1 ratio. So the moles of Fe2 plus will be 3.74 into 10 power minus 4 multiplied by 5. That will give us the moles of Fe2 plus ions. So the answer is 1.87 into 10 power minus 3 moles of Fe in 25 centimeter cube. Now understand, we have just taken 25 centimeter cube, so it is 1.87 into 10 power minus 3 moles, of the Fe2 plus ions. Let's see. Next, calculate the MR of FeCrO4, that is the compound of iron and chromium, and use your answer to deduce the value of N. Okay, now here if we have got the moles of Fe, now in the compound there is only one Fe used. And also understand, these are the moles of Fe in 25 centimeter cube only, but our total solution of F was 250 centimeter cube. So for 250 centimeter cube, the moles, that is the moles of Fe will be 1.87 into 10 power minus 3 multiplied by 10. Now that ends up with 1.87 into 10 power minus 2 moles of Fe. Now if these are the moles of Fe, obviously the moles of the whole compound is also the same because there is only one Fe in the whole compound. So the moles of FeCrNO4 is also the same, that is 1.87 into 10 power minus 2 moles. Now if we want to calculate the MR, we need to use the formula of mass upon N, that is the mass upon moles for calculation of MR. So what was the mass which was used initially, that we can find out from here, that is 4.18 gram. 4.18 gram of the mass we have used. So 4.18 divided by the moles, that is 1.87 into 10 power minus 2. Now that is equal to 223.5 grams. Now that is the MR. So 223.5 grams, that's the MR. Now calculate the value of N. Now how can we calculate the value of N? Obviously the mass of Fe, that we can have a look from the periodic table here. And yes, the mass of Fe here, we can see that it is 55.8. So let's substitute that is 55.8 in our value which we have calculated for the MR. So 55.8 as the MR of Fe. Chromium, we know that there are n number of chromium, but the mass of chromium is 52. So N multiplied by 52 for chromium. And oxygen, we know it is 16, but then 16 multiplied by 4 for the oxygen, and the total is 223.5 gram. So in this substitution, we get the value of N is equal to 1.99. So obviously value of N is 2 here. I hope the calculation is very clear. From the formula of the compound, we substituted the atomic mass of iron, which is 55.8. The atomic mass of chromium is 52, but we have n number of chromium, so n multiplied by 52 plus 4 into 16 because there are 4 oxygen atoms. Now the MR, that is the molecular mass which we have calculated, is 223.5. So substituting all the values, we get the N value is 1.99, which is equivalent to 2. So this is how we get the value of N. Here the question 4 ends, and let's go ahead with question 5 here. Now question 5 is nickel's ion, that is Ni2 plus ions form a number of different complex ions, including this nickel with the water molecules, 6 water molecules, nickel with the 6 ammonia ligands, and nickel with the En ligand, which is shown here. Now En represents 1,2-diaminoethane, which is given here. The numerical value of the two stability constants are given in table 5.1. So if nickel forms an ammonia complex, the stability value is 4.8 into 10 power 7 here, and if it forms a complex with the diaminoethane, its stability value is 2.0 into 10 power 18. Now complete the expression for the K stability value of nickel with the diaminoethane complex. So if we write an equation where nickel in the 2+ state is reacting with, you can see here there are 3 ligands used, so 3 En ligands used, then it will form the complex which is shown here. And so the stability expression, what we can write here is the nickel into En 3 to the power 2+ divided by the reactants which are on the left side. So the concentration of nickel 2+ multiplied by the concentration of En to the power of 3, because the stoichiometry of En is 3. So this is the K stability expression to be written here. Now if we have a look at the B question, a solution of a nickel complex is added to a solution that contains 0.1 moles per dm cube ammonia and 0.10 mole per dm cube of this diamino complex. Now predict which complex ion out of these two is present in the resulting mixture in the highest concentration and explain your answer. Now this depends on the K stability value of the two complex. Now if we can see here that the K stability value of the diaminoethane complex is much higher because it is 10 power 18 compared to the ammonia complex, which is 10 power 7 now. So obviously the diaminoethane complex is present in the more concentration because its K stability value is higher. So this is how we write the formula here, and the explanation which we can directly write is the K stability value for the complex, for this complex is higher or greater, you can write. So this is the explanation. Okay, the second part is complete the equation for the ligand exchange reaction occurring in 1. Now in 1, what is the reaction happening? The K stability value with diaminoethane complex is formed with the nickel of the water ligand. So now En I will write 3Y because 3 En ligands are added. So the formula of the complex we already know that we will write because that is what is formed, and the 6 water molecules are removed out by directly the diaminoethane complex. So 6 water molecules will be removed out, so that is the byproduct. So this is how we are going to write the ligand exchange reaction for this reaction. Now the C part is complete figure 5.1 to show the 3-dimensional structure. Remember this is 3-dimensional structure of the 2 isomers of this complex. Now use N to present the En ligand. Name the type of isomerism shown. The simplest way is if there are 3 En added here, it has to be shown by the 2 En line. Then the type of isomerism is optical isomerism only. So we are writing optical. It's clearly written 3-dimensional. So there has to be 2 dashed lines and the 2 bold lines which are shown here. So this is how I always prefer drawing because that makes our drawing little easier. So I'm drawing the bold lines and dotted lines first. That makes us draw it easier. Now what we know that there are 3 diamino complexes, that is ligands are present. So I'm adding all N, and now I'll add the line. So this is how I prefer drawing, making it easier. And now the mirror image of this. Obviously we'll add N everywhere first, and here all written. Now if we draw the mirror image, there has to be 1 line here, 1 line here, and the 3rd line here. So this is how we are going to draw the optical isomer of this complex. So here our question 5 also ends. So let's see what is in the next question, question 6 here. So it's figure 6.1 shows 2 reactions of ethane dioic acid. Now ethane dioic acid is having 2 COOH group on both sides. Okay, so here is the ethane dioic acid which is reacting with the SOCl2, and on the other side it's giving the products of carbon dioxide and water. Now if question 1A is draw the organic product G in the box in figure 6.1. Now in figure the box G, now ethane dioic acid is reacting with the thionyl chloride. Now thionyl chloride is a one which is a chlorinating agent, and it removes out the OH of the carboxylic acid and is replaced by chlorine. So the product also will have same, we are removing out the OH of the carboxylic acid from both the carboxylic groups, and we are adding chlorine. So this is what is the final product. OH from both the carboxylic group is removed and it's replaced by chlorine on both sides. So this is how it works. If we see the second part, it says in figure 6.1, thionyl chloride is given as a reagent that reacts with the ethane dioic acid to produce G. Identify a different reagent that also reacts with the ethane dioic acid to produce G. Now, if we are replacing the OH group with the chlorine, that is any chlorinating agent, then the other chlorinating agent is PCl5, that is phosphorus pentachloride. Now, that is another reagent that reacts in the similar way. Now, the big question is, identify two different reagents that oxidizes the ethane dioic acid to form carbon dioxide and water. Now we have said two different reagents, so we are supposed to name two different reagents. So obviously, if we want to oxidize carboxylic acids to carbon dioxide and water, one of the best reagent is acidified potassium manganate. We can also write bracket acidified, or else we can write H in H plus with the slash, that is also fine. But other than that, the carboxylic acid, especially ethane dioic acid, can be oxidized by oxygen also, but obviously that process is very, very slow. So, but finally, then oxygen also oxidizes the ethane dioic acid to carbon dioxide and water. Yes. So, C question is, the ethane dioic acid ionizes as shown, and it's given here that one of the hydrogen from the carboxylic acid is donated as H plus. Now this is a much stronger acid than a methanoic acid. Now methanoic acid is HCOH. Now suggest an explanation for this difference in acidity. Acidity in the sense that why ethane dioic is much more stronger than the methanoic acid, though on the first instance it donates just one H plus. Now the main reason for this that it has 2C double bond O group. Now that is electron withdrawing group. Now we will write that, which is electron withdrawing group, while in methanoic acid it has just one CO group. So here there are two CO group. Now what happens that because of that the OH bond weakens and the intermediate anion. Now we know that this is the anion here. This is the anion. Intermediate anion is stable. That's why it is more acidic. So for any organic acid to be more acidic, the OH bond should be weakened and the intermediate anion should be stable to be more acidic, or for it to be an acidic. So this is the 2 points you should be explaining any carboxylic acid in these terms. So let's go ahead with the next part here. Okay, here we have D question, where benzene 1,4 dicarboxylic acid. So here we have benzene, and on the first and fourth group here, first carbon and the fourth carbon, we have carboxylic groups that can be made from benzene in 2 steps. Now it's written clearly 2 steps as shown in figure 6.2 here. So in step 1 we will make an intermediate J compound, and on the second step then we will have the benzene 1,4 dicarboxylic acid. Now let's understand this point very clearly, that it's very difficult to directly add COOH group on an benzene. So what is generally done is that any alkyl group, especially methyl group, is bonded to the benzene. That is little easier, and then the methyl group is then oxidized to carboxylic acid. That is the best method of preparing and benzene carboxylic acid. So here we can do the same thing, that with the benzene we will first join the methyl group wherever we want the carboxylic group, and then this methyl group is oxidized to the carboxylic groups. So the intermediate J should be here with the alkyl group bonded to the benzene. Now identify the reagents and conditions for step 1 and step 2. So obviously for alkylation we need an chloroalkyl group. So here if we are bonding methyl group, we need chloromethane or you can say methyl chlorine, that is used as a reagent along with the catalyst aluminium chloride, that is AlCl3, and heat. That are the reagent and conditions required here. For the step 2, now we know that we are just oxidizing it, but for the methyl benzene group we need an alkaline and hot KMnO4, that is alkaline KMnO4 should be heated along with the methyl benzene, then only we get oxidize the methyl group of the benzene. So these are the reagent and conditions required. Now draw the structure of exactly one repeat unit of the polymer formed when benzene 1,4-dicarboxylic acid reacts with ethane 1,2-diol. Now ethane 1,2-diol is given here, where ethane have the alcohol group on both the carbon, and the linkage formed between the monomers should be shown fully displayed. Now that is fully displayed means showing all the bonds. Now they have said a one repeat unit. Now one repeat unit only has to be shown. So if we have an dicarboxylic acid, we have carboxylic acid on both sides of benzene, and the OH group is then replaced by the OH, or you can say that is reacting with the OH of the ethane dioic acid, ethane 1,2-diol, and that forms the water. So now let's draw the benzene 1,4-dicarboxylic acid. So here we go with the benzene 1,4-dicarboxylic acid, and I'm drawing the fully displayed form of the carboxylic part. But then, as I said, the OH of the carboxylic acid is reacting with the H of the ethane diol. So H and the OH is both removed. This is removed from the alcohol and this is removed from the carboxylic acid. So that has to be removed. Now if we remove the H from the ethane 1,2-diol, then we are left with only one O and then the CH2 group. So this is how one of the unit of the polymer is formed. Now from here again the carboxylic part will be repeated. So I hope the things are very clear, that from the carboxylic part we are removing the OH group, and from the alcohol group we are removing just the OH, and then we are bonding both the groups together, which is shown here in the repeat unit. So this is the linkage, you can say, between the two monomers, and this is the one repeat unit of the polymer which is asked here. Okay, fourth part is state the type of polymerization that occurs when benzene 1,4-dicarboxylic acid reacts with the ethane 1,2-diol. Name the linkage formed between the monomers. So what is the type of polymerization? Now we have two types of polymerization. One is addition and the condensation. Addition, we know it requires an C double bond C, that is an alkene group. Here we don't have alkene, we have carboxylic acid and alcohol. So the type of polymerization is the condensation polymerization, and the linkage here which is formed by the carboxylic and alcohol group is called the ester linkage, because that's the ester formed when carboxylic acid and alcohol reacts with each other. So here our question 6 also ends, and this is where I'll stop for now, and in the next video we'll be discussing the remaining questions.